Susana Garcia Lopez from Heriot-Watt University in the UK. Susana is a trained chemical engineer, and she's very well known for her work in carbon capture and storage and sequestration. And we're very much looking forward to her talk. She will give us insights into a systems chemical approach to MOF design. The stage is yours.
Thank you. No worries. Good morning, everyone, and it's my real pleasure to be here today. Thanks very much to Tony, the board, and the organizers for having me. And as you can see from the title of my talk, which is From Concept to Application, a Systems Approach to MOFs Development, what I'm going to be talking about today is really an overview of our work over the past 5-6 years when it comes to materials discovery and advancement of solid-based carbon capture technologies for separating CO2 from different gas streams. So I would like to start by thanking the Prisma team, which is the project that I will be mainly discussing today. And they are the real ones that get their hands dirty in the lab and the computers, and I'm really, really grateful to them for all the work over the past years. It has been an absolute pleasure to work with all of them. So let me just very briefly give a little bit of context as why we have been focusing on carbon capture, utilization, and storage technologies. I'm pretty sure that everybody in the audience have seen these type of graphs, right? They are published by different agencies, different bodies, and we are all very aware of our greenhouse gas emissions, that we need to comply with our net zero targets. In most of the countries, those need to be obeyed by 2050. And there are a series of mitigation options out there that are considered, and all of them are needed because, very simply, what we are talking about here is about abating gigatonnes of CO2 per year, so millions of CO2 per year. So this is a phenomenal task. So any help we can get from all the very different options that we've got out there are very welcome. We should all make sure that we work towards that together. So, of course, we can do a lot of things in terms of improving energy efficiency, reducing or eliminating the carbon content from our energy sources, but also one of the technologies that is on the table is carbon capture, utilization, and storage. And even with all those mitigation strategies, what it seems clear is like we have put so much CO2 in the air already that even if we do all of these, we are not going to be able to meet our net zero targets by 2050. So we actually have to remove CO2 from the air, what is called direct air capture, if we want to get there. So I've been working, pretty much all my academic career on CCS technologies, and different materials, different processes. And we always had this very big question, right, when it comes to what's the optimal technology, what's the optimal material for a given application. And what you see here is a GUI schematic that we put together back in 2019 when we happened to gather a couple of colleagues, and we started thinking about, okay, we've got all these options when it comes to CO2 sources. There are also many different things that you can do with your CO2, right? So depending on what that CO2 source and what that CO2 sink is and where you are in the world, and that has a huge impact, I'll show that a little bit later on, what's the optimal solution? That's what we kind of ask ourselves, and can we come up with a way to answer that question? So we envisioned then to design a tool that would be able to provide answers to all the different questions that the different stakeholders within this field, this CCUS field, have. And the questions from the very different stakeholders are very different. You see them here, like, you know, in a cartoon, kind of showcasing the different, what we call spheres, and we define this as the stakeholder universe of carbon capture. So the questions that, for instance, a CO2 producer or a material chemist or an engineer or an economist has are very different, and there wasn't a tool out there, a mechanism out there that would allow us to answer all those questions from a holistic or a whole systems approach. So then what we envisioned then was the creation or the development of what we call our Prisma platform. Prisma is the acronym for the project that was founded back in 2019, finished a year and a half ago. And what we envisioned there was to come up then with this tool or this platform that what it would do is to allow us to discover materials. So it's a materials discovery platform that will be able to identify an optimal solution, an optimal process, and an optimal material for a given case study, where a case study, as I've mentioned earlier, is defined by a source, a sink, and a region in the world. And we did that by integrating all the way from the materials to life cycle assessment and going through the process and the techno-economics. All of that integrated in a consistent and a robust manner, so we can very quickly get a feeling of whether a particular technology based on a solid sorbent is a solution for our specific case study. As you can see from the slide, this is something that, of course, one single team cannot do, or at least I don't know of any single team that has the expertise in all these different areas to be able to put this together. So what we did is, of course, we got together a series of partners from Europe and the States to work on all these different aspects and integrate all this different knowledge. I was the project coordinator. I had the pleasure to work with all of them. But what I can tell you is that it was extremely challenging, very rewarding as well, but extremely challenging to just at the very beginning to make sure that we would understand each other. Because when an engineer would say porosity, the chemist would understand something else, and the LCA people would understand a different thing. So we were all in like these meetings that were going on, and we couldn't even understand the word. So it was an extremely interesting experience. So, so the results, the main results that I will be showing today were published last year. The paper is open access. You've got there all the details when it comes to all the different models that we have developed, the validation, etc., and a very nice interactive tool also to have a look and explore all the results if you are interested. So we developed the Prisma platform with a focus on specific solid sorbent materials, which are metal-organic frameworks. And the fantastic thing of speaking after Mohammed and Omar is that I don't need to explain anymore what a MOF is, because they have beautifully explained the beauty and the advantages of MOFs. So in principle, you have all these materials with different metals, different ligands, different topologies. And for us, it was the perfect play field to incorporate in the platform, because basically it would give us this huge chemical design space that we could explore for many different applications. And of course, the key question there was, okay, out of, in principle, you heard before that we've got millions of possibilities when it comes to MOF materials. What's the optimal, or how to select what's the most appropriate one for a given application? And this is something I would like to highlight a lot, in the sense that a material needs to be developed for a specific application. So the process and the material design needs to go hand by hand. So how does the platform look like? How does the data flows in between what we call our layers? And this is something that it's represented here. As you can see, it's a quite dense slide, but basically what I'm trying to show is how the amount of data, first of all, that we need here, we needed to put here in order for this analysis to be done, was really enormous. How we spent an awful amount of time gathering all the information, huge amount of databases to be able to do all this analysis in an integrated manner and in a consistent manner. And what you see here then is that what we calculate first in our materials layer are the material properties, and this can be obtained either experimentally, so even though we developed our platform with MOFs, if you work, say, in any other particular material, you are an experimental chemist and you've got the data, you can directly input the experimental data into the platform, and then that material can be ranked for all the applications that we have developed in the Prisma platform. But equally, we can input that data from molecular simulations. Then in the process layer, we get all those properties, and basically we look at the evaluation of the process. So we need process and equipment data, and then we look at many different process configurations as well. So process, temperature swing adsorption, temperature vacuum swing adsorption, different processes there that you can consider depending on your source and your sink. Then in the techno-economic layers, we make use of process and data for utilities and economic data to then assess the economic performance of your plant. So basically from here, in the process layer, we look at a single column, and then we scale up from the process to the TA layer to then come up with the number of columns, number of trains that you need in order to process the specific flow rate that we've got in our host plant. And finally here, we've got the LCA layer, where we actually take into consideration a full life cycle assessment. So we consider material synthesis, use phase, and disposal when we look at our MOF materials, but of course we also have all the data for the life cycle impact assessment and life cycle inventory that is required for our predictive LCA models. What's the output of the platform? So you have it here, a combination of 50 different key performance indicators from the different layers that gives us different insights into the process. So in the paper that I've mentioned earlier, we presented the results for 66 different case studies that we ran in the Prisma project. The focus of the project at that time was carbon capture from point sources, and we looked at mainly 3 different CO2 sources with 3 different concentrations, different type of processes in the process layer when we regenerate the material by either swinging the temperature or by either swinging the pressure at different levels of pressure. We looked at 5 different regions in the world, UK, US, 2 regions in China, which were very interesting for us to explore because they are very different when it comes to the carbon intensity of their electricity grid, and then Switzerland. And we also looked at different utility systems. So it's very important when you design a carbon capture plant that you take into consideration if you've got something already available at your host plant that you can take advantage of, because then that can hugely reduce the energy consumption that you required for the regeneration step. So in all these case studies, the CO2 sink was just a single one, geological storage. And let me show you next. Let me exemplify with a particular case study what are the type of results that you get out of this platform. So in this specific case study, we look at capturing CO2 from a cement plant, so approximately 20% CO2 in the flue gas stream. We send it for CO2 geological storage in the North Sea because the plant is located in the UK, and we screen the database of approximately 1,200 MOFs in this exercise. So what was the first thing or first question that we got asked ourselves? As I've mentioned, we get 50 different KPIs out of the platform, and the very first question was, which in principle you've got 50 different metrics to assess the performance of the material or to drive that materials discovery process. So which KPI should we make use of, or which KPIs? And what you see here is like we did this exercise of, well, we selected a few. This is based on some statistical analysis that we did. We selected a few of those KPIs, and then we looked at the ranking of the materials based on those different KPI values. So here what you have is the ranking of the database, approximately, as I said, 1,200 materials, versus the 6 different KPIs that are coming from the 4 different layers. If you were to look at the top performing materials according to selectivity, this is this S here. Selectivity is a very simple metric that is very commonly used, has been very commonly used in the literature as a KPI to decide on what are the promising materials for carbon capture applications. So top 10 performing materials according to that KPI would be these blue ones, top blue ones here at the top. So if you were to track down the performance or the ranking of those materials according to the other KPIs, you see how much the ranking changes. So many of those would do quite poorly, in the TA layer or in the all over the place in the LCA layer. So you can, of course, do exactly the same exercise for any of the other KPIs, and you can see a similar trend in the sense that ranking changes. Maybe not as abruptly as for the selectivity, but it does change. What are we looking for here, ideally? So ideally, of course, what we would like to have is a material that ranks very nicely at the very top and in a flat trend, right? So basically it ranks well in all the different aspects, in all the different layers and KPIs. But that's normally very challenging to get. So for us, the ultimate KPI that drives our materials discovery process is what we define as our NCAC, or net carbon avoidance cost in euros per ton of CO2. And you see here the definition. It's the overall cost incurred in avoiding a mass unit of CO2 into the atmosphere over the entire life cycle of the process. So we consider in this definition absolutely all the different aspects of the Prisma platform. So we want to make sure that when we design a carbon capture process with a specific material in a specific region of the world, we can compete with the current state of the art. And this is what you see here in this graph. You see the NCAC value versus, a couple of KPIs from the process layer, recovery and specific electrical energy, and each dot in this graph is one of those 1,200 MOF materials in our database. And what you see in with this red dotted line, that's the cost for the same process with the state-of-the-art carbon capture technology, which is based on solvent systems, so MEA-based system, which is up and running in many plants. So that would be the actual cost with that state-of-the-art. And of course, we want to make sure, I'm a chemical engineer by background, so I'm trained with the mindset of you don't do things if it's not economically competitive, because if there is a solution already out there that can give you a better option, why would you bother? So then, in principle, all these materials that you see here can provide or can outperform the state-of-the-art out there. Many of them by as much as 50% in terms of cost reduction. So huge impact or potential for solvent-based carbon capture technologies for this specific case study. Of course, this is an in silico platform, so the modeling team have done all of this on the computer, and when you go and present this, the first question is how accurate or how reliable your results are, right? How do you know that we can trust them? And that's exactly what we did. So we did a lot of validation, not only at each individual layer of the platform, but also we corroborate and double check with a lot of experimental data. And we specifically looked into the whole performance of a couple of different MOFs. One of them is CALF-20, very well known in the MOF community because it's used at a commercial scale in a cement plant in Canada. And then another one, MIP-212, that came out from our materials discovery process. And we were very pleased with the results when it comes to the agreement between the experimental and the simulated results. So that encouraged us a lot in terms of all the work that we had put into designing the platform. So as I mentioned earlier, so the idea here is to provide this tool that you've got a specific question, regardless of what type of a stakeholder you are, and you can go and get an answer. So for instance, if you are an engineer like me, that the type of questions that we are interested on are, what's the best technology for a given separation? How do we scale up the process? All these type of things. So we looked at different technologies for 3 different case studies. You see it here, the NCAC value versus the 3 case studies where we separate CO2 from NGCC, coal and cement, and we looked at 3 different technologies, and of course we compare with the benchmark. So what you see here in these violin plots are the performance of the top 20 materials, top 20 performing materials identified by the platform. And very quickly, what you see is like when you have a higher CO2 concentration in your gas stream, solid sorbent base separation technologies are very favorable when it comes to potential cost reduction. You see it here, how far we are from the dotted lines. As the CO2 concentration in the flue gas stream gets reduced, so we are moving from 20% to 14, 15%, and to 4%, you see how this gap starts reducing. So we are not that competitive anymore, to the point that under 4% CO2 in the gas stream, we start struggling. So we need to become more, more original, more sophisticated when it comes to the type of process that we need to design in order to take advantage or exploit the characteristics of the materials. So again, very quickly, you get a feeling of what you need to focus on. Equally, if you were to look at the environmental perspective, so we would like to understand what are how to maximize the amount of CO2 capture. So basically, how to make sure that running a process plant, running a carbon capture plant also generates CO2 emissions, because you also need to produce your materials, you need to build your plant and everything, and that needs to be considered, because basically you need to ensure that by constructing, operating a pilot plant, a capture plant, you are not producing more CO2 than what you are capturing. So this is what the LCA layer takes care of. And not only, of course, in terms of the CO2 equivalent emissions, but also many other impact categories that we need to look at. So something that we obtain from the analysis on the LCA layer are indicators or KPIs like the climate change or the effective recovery. And what this gives you is a very quick idea of what's the impact. Here we show that climate change KPI, which gives you an indication of, for every 100 captured CO2 molecules, 100 times that climate change indicator are indirectly emitted. In other words, this KPI changes between 0 and 1. Ideally, you want it to be 0. That means that you are not generating any indirect emissions at all. That's, of course, impossible. There are always some indirect emissions linked to your process. But the worrying thing is that if you go beyond 1, that's where you need to get worried, because then you are generating more CO2 than what you are capturing. So again, here we looked at the analysis for the 3 different CO2 sources. Here we fixed already the technology based on our analysis earlier, and we look at the 5 different regions I mentioned earlier, and you can see what's the impact of building and operating a carbon capture plant in a different region of the world. And the amount of indirect emissions varies hugely depending on where you are. You see here, for instance, almost hardly visible, for instance, Switzerland, which is very ideal in terms of indirect emissions, because the carbon intensity of the electricity grid is very, very low. So that gives you, a CC KPI very close to 0. And of course, that's inversely related to the effective recovery, because then you need to discount those indirect emissions from your process recovery. So what type then of insights you get very quickly from this exercise in the platform? So things, for instance, like this one in this graph. What you see here is, again, the ranking of the material versus the 6 different KPIs that I mentioned earlier, and all the red lines here indicate those materials that when you operate them, for this specific case study, with whichever process you have been looking at, generate more CO2 that it captures. And what you see is actually quite a few of them rank very highly or very top in selectivity. So we really need to be very careful and ideally consider this holistic approach from as early as possible in the materials design space. So we make sure that when we move from the screen to the lab and further on, when we start scaling up, we are investing our efforts, our money, our time in materials and technologies that are worth it. So if we look at the results from an investor's perspective, what's the kind of most convenient or ideal place to install a carbon capture plant. You see here the analysis for, again, the 5 different regions. And what you see is the cost of carbon capture here in euros per ton. And this is actually, if you are, if you are in this field and you have a look at the literature and you check this type of values, this is normally the value you find. It's basically you look at all the boundaries merely around your carbon capture plant, and that's where you base your techno-economics on. But, and you see how the value changes for the different sources. Of course, the more concentrated the CO2 in the gas stream, the cheaper the separation. Yes, pure thermodynamics, it's easier, right, than when you go to more dilute solutions here. But what you see here, the difference between these two graphs is only one word, right? This net, this N at the beginning of the CAC. And again, this NCAC takes care of everything else that we consider in the platform, and you see how much the cost can change, up to 50% more, depending on where you are in the world, if you consider everything that you need to be considered. So we need to always be very careful when we compare cost values. We need to very clearly understand what's the boundary of the analysis, what are our assumptions, and so on and so forth, to try to be able to compare apples with apples. So, of course, this is a modeling exercise, and we did our very best to calculate all those properties, all that data that we needed to input in all our different databases for all the different layers in order to be able to make this assessment. But there are properties, we are very well aware of those parameters that we cannot calculate because simply we just can't. For instance, the cost of the MOF. And this is because I always get this question. Now I have in a slide, so it preempts the Q&A. So the question is always, which cost of the MOF have you considered, right? And we are talking here about the screening, databases of thousands of materials. Many of them haven't even been synthesized yet. So how do you come up with the cost of the MOF? I would be interested in your opinion, Omar. Because, we looked at what's already out there, MOFs that have been commercialized, that have been scaled up, and that's what we took as our base case value. And this was a value of 30 euros per kilo. So, as I said, you need to make assumptions. For engineers, making assumptions, that's what we do every day. I mean, we never have all the data we need, so you have to always make assumptions. But what you can do is then you can assess the validity of your assumptions, and we've done a lot of sensitivity analysis around all those parameters that we were not certain about or that we had uncertainty, and then we looked at the impact of those assumptions in our final KPI. And what you see here is precisely that exercise for the cost of the MOF. So what you see is like in our base case, we consider 30 euros per kilo. If we were to negative and we can actually synthesize a MOF that is cheaper, we see that that leads to a 7% drop in our net carbon avoidance cost. Equally, if we were too optimistic, then we can see the increase in the NCAC value. And we can do the same. Another parameter that we cannot predict, or not so far, is, although we are trying to come up with clever ways of doing so, is a solvent's lifetime. So how much or for how long you can keep your material operating in the carbon capture plant before you need to replace it. Again, this is super difficult to estimate beforehand, just based on a crystal structure. And what we did again was to make an assumption of 5 years. Again, this is informed based on what's going on in the industry, and then we change that value to assess the impact on the cost, on the NCAC. So something that hopefully you've got by now a kind of a clear picture of what we are trying to do here. And something we faced, and it was actually quite challenging, is that because we needed so much data in order to start getting the results for our case studies, but equally we were generating so much data as well. So we were overwhelmed by data, literally overwhelmed in terms of, okay, how to make sure that we take advantage of all of this that we are generating, but also that we learn as much as possible from all the different case studies. So we have made use, very early in the project, we started making use of artificial intelligence for all different sort of purposes, all the way from, for instance, predicting the oxidation states of the metal in our MOF, which is something that, you know, the molecular modelers need to know in order to carry out their simulations, to also predict the heat capacity of the materials, to increase the diversity of our databases, but we also make use of other models like LLM models to harvest the literature and try to predict synthesis conditions, identification of the genes of the materials. So we are interested in, okay, if we've got this whole bunch of materials that are top performing for a specific application, they must have something in common, right? So what is it that they have in common? Can we learn from that and leverage on that? Also design of experiments. So we really have made use of AI for many different purposes. It really has helped us a lot in terms of advancing at a faster pace, but also in terms of understanding what was going on. So just as an example of one of the specific applications where we made use of AI was to actually increase the diversity and the amount of top-performing materials for our case studies. And this is what you see here in this schematic. So for this specific case study, as I've mentioned, we started with this data set of MOFs. And normally what happens when you run a case study is that you get those nice plots that I showed, but you are only interested in really the materials at the bottom that give you the lowest cost. And normally those are not many. And we want to make sure that we increase the size of that, of that type of materials, because we are here working on a computer, and by the time we reach the lab, and by the time we scale up, you are going to be losing materials throughout the way. So we need to make sure we've got enough materials in that space to ensure that at the very end of the road, we end up with a few successful ones. So then what we did here then is like, we develop a NCAC predictor, so we develop an ML model that would be capable of predicting the net carbon avoidance cost for a given MOF, just based on the chemical structure. And then we made use of that predictor to apply that to a large MOF database. So we are moving now here from approximately 1,000 MOFs to 30,000 MOFs. And that, what it allows us was to then obtain more of those MOFs that are the ones that are top performing for our given application. What's the result of this exercise? This is an iterative approach that what it allows us to do was to then start moving from, you see it here, the distribution of the top performing MOFs from the original round, let's put it this way, and then when we are starting carrying out more and more rounds, what you see is like we start populating the violin towards the bottom, so you know it becomes kind of fatter and more here towards this bottom. So we are getting more and more materials in this space, which is exactly what we were hoping for. And then when you translate that into the materials or chemical design space, what you normally observe is that they are lumped together in a specific regions of that chemical design space, and there is where we apply all our adsorbafor concepts to understand what is it that they have in common. So this all was carried out under the PRISMA project, as I mentioned, 66 different case studies, and in recent years, well, now for 2 years, approximately 2 years and a half, we have been expanding the platform to direct air capture applications. I mentioned that at the beginning, and it's extremely challenging to separate CO2 from the air where you only have 400 ppm CO2. And if you remember from my graph at the beginning, when I compared the technologies for different CO2 sources, you started struggling when the CO2 gets more and more diluted in the gas stream. So you need to become more clever in the way of designing the process and taking advantage of the material's properties. So what we have been doing in Use of DAC is the follow-up project from Prisma. It's funded by the Grantham Foundation in the States, is to try to very firstly understand, because of course we had all the workflow in place, all the platform in place for MOF materials, and all of them are physisorbents, the ones we have in our databases. We started by looking at, okay, is it possible to design a DAC process based on a physisorbent? And if you are familiar with the DAC space, mainly chemisorbents are the materials that are considered for this type of application because of the affinity for CO2 under such a dilute concentration. So is there a hope for a physisorbent to in a DAC process? And in principle, it can bring a lot of advantage in terms of energy reduction and cost. And what you see here is just a bit of some of our latest results when we did this exercise. These are the specifics of the case study we looked into. This is in Norway. We make use of a heat pump to provide the energy for our process, and we send the CO2 to the Northern Lights saline aquifer, very well known in the CCS community. And again, here what you see is the net carbon removal cost. Now we move from net carbon avoided cost to net carbon removal costs, because we are removing CO2 from the air, versus, again, a couple of different KPIs. Here is where we are today with our exercise, so between 200 and 300 euros per ton. Here is what where we are hoping to get based on all the activities that are going on. So something else that I haven't discussed today, but I would really like to mention, is that, of course, I mainly focused on the results from the platform, from the modeling exercise, but we have a huge and fantastic experimental team that is working alongside the modelers that get our top-performing materials, what we call our lists of top-performing materials. They go into the lab, synthesize, characterize, performance test, etc. So. And very quickly, before I wrap up, I would like to just mention briefly what are our current efforts when it comes to extending the platform to scenarios that are relevant to the UAE. And I'm very fortunate to have a PhD student based here in Dubai. Heritage University has a campus in Dubai. And Ashna Nisar, who is in the audience, and she has a poster straight after this session, has been looking into what are the specifics of the UAE in terms of the energy landscape and how to expand the Prisma platform to scenarios that are relevant here. Of course, CCS is very relevant here, and these are all the things that she's looking into when it comes to the different case studies for the UAE. And you see here things like the relevant point sources that we are looking into, equal industrial applications, so steel, aluminum, and cement are very relevant industrial plants here in the UAE. And then very interesting case studies where we've got novel carbon sinks, so we send the CO2 for mineralization, and also we integrate DAC with desalination plants in order to get materials for the construction industry. So really fascinating case studies that Asna is looking into, and we are extending the Prisma platform for. And the very final slide is touching a bit on our big vision here. And when we developed the Prisma platform, we focused on carbon capture applications because, that was our expertise, that was our main focus. But we always developed it with this big vision to expand it and extend it to many other different separations, materials, etc. So the way we then built the platform is in a very modular way. So all the different layers are built up with modules. So basically, you can plug in and out different modules in the different layers that enable you to leverage or benefit from the backbone of the platform, but then extend to other relevant applications. This is just an example on hydrogen storage, where we are looking at storing hydrogen in MOFs for backup power applications. I will not spoil the results because Ashna has a poster on this, so feel free to stop by her poster and she can give you all the details. But again, just an example of how we can expand to many other different type of applications. So what's next for us? Well, in principle, a lot of things that we have in the pipeline and we would like to explore, all the way from systematically extending and improving the platform. A lot of also AI embedded in our future activities, and also extension to other type of materials that could be promising for this type of energy-related applications. And with this, I would like to thank, of course, all our founders for supporting us over the past 5-6 years, and they keep supporting us. And of course, we wouldn't be able to do it without them. Thank you very much.
Thank you very much, Susana, for this brilliant talk. Questions? There's one over there. Okay, Mohamed, I think you have the mic. That's fine. Sure.
Thank you, Susana. I have a couple of questions, but I will limit it. When you showed as you get lower in concentration of CO2, like in GCC, you have another problem that you didn't touch on, which is you have a lot of oxygen in there. Did you actually assess the stability of those materials on oxygen? And as you know, not too many of MOFs are stable in presence of oxygen. That's one. And the second question, since I have the microphone, when you talk about the DAC, now you said you need to have your predictors to derive the CO2 absorption and the Henry Lofzer selectivity to have very sophisticated Monte Carlo models and DFT. Did you see any discrepancies when you get to DAC that it doesn't work?
Okay. Yes, thank you, Mohammed. The first question, the modeling exercise is based on ternary gas mixtures that contain CO2, nitrogen, and water. So those are the three components we consider for computing all our mixture data and everything. And then when we looked at the other contaminants, we kind of look at those in the next step. So our first initial screenings are really to screen out, if you wish to call it like that, in terms of identifying the bunch of materials that we need to study deeper. So there we start applying more detailed models, and we start looking into all those type of things. But there we are already kind of looking at experimental data rather than predicting that with, for instance, molecular simulations. So we kind of funnel through the materials, and then we start looking at more and more of those details as we go through the funnel. So that's the approach we have followed, because basically our lesson was that if from the very beginning you try to embed all the complexity that we have in the system, it's very difficult to arrive at sensible results.
No, I understand that. I mean, you have CO2, nitrogen, water, that's normal. But in GCC, you have 10% oxygen. So it means in your predicted materials, did you actually add the oxygen component or not yet?
No, not yet.
Because that's the problem with GCC, is not getting the material, is the oxygen is the problem.
We have the same challenge in DAC. So basically, when we started looking at DAC, really the problem there is not so much the CO2, but the water. Absolutely. So yes. Then, of course, we had to change a lot of things for the DAC case studies, starting from the type of contactor that we were using, the type of regeneration strategy, but also there, the modeling of the water in the material is a nightmare. I know, yeah. Not only from the modeling side of things, but also actually from the experimental side of things as well.
So how do you do the modeling actually? Do you look at the competition of water and CO2 during your thing?
Yes, okay. That's right.
Thank you, Suzanne. Thanks.
Hello. Thank you, Susana, for your nice lecture about Prisma platform to select the material. So, apart from the MOF, can we use this platform for other materials?
Yes, absolutely. As I've mentioned, we developed it with MOFs for many different purposes, but there are different routes to enter materials data into the platform, and you can either, if you got your C file, that's something that we get straight away, and then you can just assess the material for a given application. So you can actually input any type of material. We've got different entry points depending on which data you have.
Okay, thank you.
I think there was a question over there, or is that the lady over there? No? Okay, good. So if there are no more questions, then let's thank all speakers of this session again. Thank you very much. And we'll see each other at the poster session. Thank you.